Hi everyone, my name is Yusuf Fakhr and I'm a student at Dalhousie University in Halifax, Nova Scotia. In this video, I'll be walking you through my second field experiment for my intertidal ecology and diversity course. This experiment looked at whether wave exposure affects barnacles percent cover on rocky intertidal shores at Point Pleasant Park. Let's get into it. Before I begin, I want to take a moment to acknowledge that Point Pleasant Park and Dalhousie University are located on the ancestral territory of the Mi'kmaq people. The Mi'kmaq have been the stewards of this coastline, its waters, and its ecosystem for thousands of years, long before any scientific study of these shores began. I am grateful to conduct my research on this territory, and I carry that gratitude with me throughout this work. Point Pleasant Park, also known as Amnugati, is located in Halifax, Nova Scotia, and was established in 1866 on traditional Mi'kmaq territory, which holds cultural, historical, and ecological significance to the Mi'kmaq Nation. To understand my experiment, we first need to talk about the intertidal zone. The intertidal zone is the area of the shoreline that is exposed at low tide and submerged at high tide. It is one of the most physically challenging environments on Earth. Organisms living here must survive desiccation, temperature extremes, and the consistent force of waves. The intertidal zone is divided into three main zones: the high zone, which is exposed the longest and experiences the most desiccation stress; the mid zone, which is between the tides and is where barnacles dominate; and the low zone, which is submerged most of the time and is covered in mussels and algae. My experiment focused specifically on the mid intertidal zone. The organism I studied is Semibalanus balanoides, the acorn barnacle. These small crustaceans permanently attach themselves to rock surfaces during their larval stage and never move again. They are filter feeders, which means when they are submerged, they open their shell plates and extend feather-like legs called cirri to sweep food particles from the water. Barnacles rely on fluid dynamics to capture food, using their cirri to generate feeding currents. Barnacles are incredibly common on rocky shores in Atlantic Canada and are often used as indicator species for environmental conditions. Their distribution is influenced by many physical and biological factors, including wave exposures, which is exactly what I investigate. My research question was, does Semibalanus balanoides percent cover differ between wave-exposed and wave-sheltered rock faces in the mid-intertidal zones at Point Pleasant Park? And my null hypothesis was that there is no significant difference in barnacle percent cover between wave-exposed and wave-sheltered mid-intertidal zone faces. In other words, I expected to find a difference, but scientifically I had to test whether that difference was real or just random due to chance. My study was conducted on June 6, 2026 at the shoreline of Point Pleasant Park in Halifax, Nova Scotia at approximately 44 degrees 37 minutes north and 63 degrees 33 minutes west. I worked within a 3-hour low tide window, arriving at 7 an hour before the low tide and finishing around 9:30 to 10 p.m. Arriving early gave me the time to identify the mid-intertidal zone boundary by watching where the waterline was sitting and observing the barnacle band on the rock face. My experimental design compared two naturally occurring treatments: wave-exposed rock faces and wave-sheltered rock faces, both within the mid-intertidal zone. Wave-exposed faces were rock surfaces directly facing the open surface that receives the full force of wave action. Wave-sheltered faces were rock surfaces tucked into surfaces or facing away from the water, where wave action is reduced. Crucially, both face types were at the same tidal height, within plus or minus 0.1 meters of each other. To control for tidal height as a confounding variable, I placed 5 quadrats on each face type along a 5-meter transect, giving me 10 quadrats in total. Before heading to the field, I used a random number generator to pre-select the meter marks for each quadrat, and at each mark I flipped a coin to decide which side of the transect to place the quadrat, left or right. This ensured that true randomization and avoided any bias in the quadrat placement. So for each quadrat, I placed a 20 by 20 centimeter frame on the rock surface and photographed it directly from the top with my phone. And back home, I opened each photo in Fiji, which is a free open source image analysis software, and overlaid a 5x5 grid on the photo, dividing it into 25 equal cells. I then scored each cell as either barnacle covered, giving it a score of 1, or not covered, giving it a score of 0. Percent cover was then calculated as the number of cells covered divided by 25, and then multiplied by 100. So for example, if 14 cells were covered, then 14 divided by 25 and then multiplied by 100, which would give me 56% barnacle cover. So these are the screenshots of how I used the Fiji software to count. See how inside the 25 cells some have green arrows. These were marked as full cell that has more than half barnacle cover, and those that are not marked with the green arrow, these are given a score of 0. So on the left side for the sheltered face analysis, we have 1, 2, 3, 4, 5, 6, 7, 8. So that would be 8 divided by 25 and then multiplied by 100. Before running any statistical test, I checked the assumptions required for a t-test. First, I ran a Shapiro-Wilk test on each group to check for normality. That is to check whether the data are approximately normally distributed. Both groups passed. Second, I ran a Levene's test to check for equal variances across the two groups. This also passed. Because both assumptions were met, I used an independent sample t-test with equal variances to compare mean barnacle percent cover between the exposed and sheltered groups. All analyses were conducted and performed in R. Before that, let's look at the results. The bar chart on the left shows the mean barnacle percent cover for each face type, with error bars representing plus or minus 1 standard deviation. The exposed phase had a mean barnacle cover of 64.80%. The sheltered faces had a mean of 41.60%. That is a difference of around 23% between the two faces, which is quite substantial. Just visually, you can already see a clear difference between the exposed and sheltered faces. Turning to the statistical results, the independent t-test gave a t-statistic of 4.5853 with 8 degrees of freedom and a p-value of 0.00179. This is well below our significance threshold of 0.05. Therefore, the null hypothesis is rejected. Wave exposure does have a significant effect on barnacle percent cover at Point Pleasant Park. So how do our results fit with other researchers and what they have found? Jenkins and Hawkins found that in Northwest Europe, barnacles are extremely abundant on wave-exposed shores, but rare on sheltered shores, and that larval supply is key limiting factor on sheltered rocky shores. This directly supports our findings of higher cover on exposed faces. Restel and colleagues showed that hydrodynamics affect nearly every aspect of barnacles' lifestyle, including larval recruitment, feeding behavior, and morphology. As sessile suspension feeders, barnacles must cope with shifts in flow regime throughout their lifetime. This tells us that water flow is a fundamental to barnacle success, and exposed faces have much more of it. And Scrosati studied semi-balanus balanoides on wave-exposed bedrocks on the Atlantic coast of Nova Scotia, the same species and on the same coast as my experiment, confirming that this species is well established in wave-exposed intertidal habitats in our region. Overall, our results are entirely consistent with the existing literature. So, why exactly do exposed faces have more barnacles? There are 3 main biological reasons. First, more food. Barnacles are filter feeders and dependent on water flow to deliver food particles. Wave-exposed faces receive constant, strong water movement, bringing in a continuous supply of phytoplankton, while sheltered faces have much less water movement, meaning less food reaches the barnacles there. Second, more larvae. During the barnacle settlement period, larval barnacles are carried in the water column. Stronger wave action on exposed faces deliver more larvae to the rock surface, leading to a higher initial colonization. As Jenkins and Hawkins showed, larval supply is actually a limiting factor on sheltered shores. Third, algae blocking settlement on sheltered faces. The sheltered faces in my study had noticeably more algae, particularly fucus and Ascophyllum nodosum. These algae physically sweep barnacle larvae off the rock surface with their fronds before the larvae can attach, further reducing barnacle cover. Together, these three mechanisms create the strong difference in barnacle cover we observed. Like any field study, this experiment has limitations that should be acknowledged. First, my sample was small, only 5 quadrants per group. With n equals 5, statistical power is low, which means there is risk of either missing a real difference or overestimating one. Second, I sampled on a single day, June 6. Barnacle percent cover can vary seasonally with recruitment pulses and winter die-off, so my results may not represent conditions at other times of the year. Third, although using Fiji standardized my scoring, there is still some subjectivity in deciding whether a cell is covered or not, particularly near boundaries between covered and uncovered areas. And fourth, it is very difficult in a field setting to find a truly sheltered face. My sheltered face reduced wave exposure but did not eliminate it completely, which then inherent limitations of comparing natural microhabitats. I want to spend a moment on the principle of two-eyed seeing and Mi'kmaq, which was brought forward by Elder Albert Marshall of the Mi'kmaq Nation, as described by Bartlett, Marshall, and Marshall in 2012. Two-eyed seeing refers to learning to see from one eye with the strength of indigenous knowledges and ways of knowing, and from the other eye with the strength of Western science, to using both eyes together for the benefit of all. For my experiment, this means not treating barnacle monitoring as purely Western scientific exercise. The Mi'kmaq people have observed and interacted with this coastline for thousands of years. Their knowledge of seasonal patterns, tidal rhythms, species behavior, and coastal change is a distinct and complete knowledge system, not just supplementary information. A truly two-eyed seeing approach to intertidal research would involve Mi'kmaq knowledge keepers as equal partners in the study design, data interpretation, and decision making, not just as consultants. This is something I want to incorporate in any future work. Building on this experiment, I have 4 recommendations for future work. First, increase sample size to at least 15 quadrants per group to improve statistical power and reliability. Second, repeat the study across multiple seasons to capture temporal variation in barnacle settlement and cover. Third, and most importantly, partner with Mi'kmaq knowledge keepers in two-eyed seeing framework to incorporate traditional ecological knowledge into long-term barnacle monitoring programs along the Nova Scotia coast. And fourth, use barnacle percent cover as a bioindicator of coastal health ecosystem. In conclusion, this study found that barnacle percent cover was significantly higher on wave-exposed rock faces at 64% compared to wave-sheltered at 41%, and the mid-intertidal zone at Point Pleasant Park. An independent sample t-test confirmed this difference was significant. It was statistically significant. Therefore, the null hypothesis was rejected. Wave exposure is a significant driver of barnacle distribution at this site, consistent with established intertidal ecological literature. Future work with larger sample sizes, repeated seasonal surveys, and Mi'kmaq knowledge partnerships would greatly strengthen these findings. I would like to thank my instructor Isabel and my teaching assistant Freya at Dalhousie University for their guidance, feedback, and help throughout this course. Thank you to my field companion Hadi for coming out to Point Pleasant Park with me and keeping me safe. Finally, I want to acknowledge that the Mi'kmaq people whose territory this research was conducted on, I am grateful for this opportunity to learn from and explore these incredible intertidal ecosystems on their land.